Let's settle down. So welcome everybody to the CFA Colloquium. Our speaker this week is Matt Evans from MIT. Matt did his PhD work at Caltech, where he worked on the LIGO detectors, on various aspects of LIGO. His thesis was titled Lock Acquisition in Resonant Optical Interferometers. And we'll find out why optical interferometers when we're talking about gravitational waves. From there, he went to the European Gravitational Observatory to work with the Virgo group and joined the MIT LIGO lab in 2006. He became an assistant professor in 2013, and he's been at MIT since then. So Matt's work is on gravitational wave detectors, various aspects, and he has a lot of expertise. And he's also been thinking a lot about the future, which I think is what he's going to tell us about today.
Thanks. So, hello everybody. Thanks for the invitation. And yeah, I started with this picture because it's totally unrelated but kind of pretty. So I took this picture a few months back when the colors were great. All right, so I will talk to you about gravitational wave detection with LIGO, pretty generic title, but I've modified this talk from my usual colloquium, assuming that you guys have seen a lot of the usual stuff. So if you see me tripped up by my own slides, that's why. But anyhow, we'll get into some things that are happening in the future, not just about the past, but let me start briefly in the past because I have all these great animations. It's hard not to do this. So I'm sure that you've all heard the news. My favorite comment about this whole thing, this big media splash, actually had to do with the tweet from Obama. I'm going to miss this guy. One of my colleagues said, when Obama tweets about you and nobody died, you must be having a good day. Because it's one of my favorites. So anyway, bear with me for a few of the things most of you have already seen, and I'll just get through the introductory material and then start hitting some things you probably haven't seen. So first off, obviously, I'll talk to you about binary black hole systems and mergers of these things because this is what LIGO detected. And we have this wonderful animation that shows a pair of black holes coming together with stars behind them, and you see the warping of space-time around the black holes as they're moving. For those of you who have seen this before, you might notice some interesting features like these little guys on the sides here. That's actually the shadow of the other black hole as the light wraps around the back. Right? And this is the Einstein ring of the whole thing. You'll notice the stars in the Einstein ring move very fast right there. Right? It's kind of a singularity. Anyway. So great animations came out of the press release. The second of these is something which is more relevant to the physics I'll be talking about. So here we're looking at numerical relativity simulation of the same event, but looking at some slice through space-time and seeing how it's warped by these black holes as they come together. So here you can see the black holes going around each other up here and the warping of space-time, but look also at the waveform which is being produced down here at the bottom. So the blue is tracing out the gravitational waveform that would come from this pair of black holes as they orbit around each other and lose energy. You can see that it's moving up slowly in frequency and growing in amplitude. And then right at the end, I should also mention that this is the clock. You can see it's ticking very slowly compared to real time, and right about here it'll slow down and almost stop. This whole thing is a quarter of a second kind of time. So it's very rapid at the end of the life of these black holes that have been presumably going around each other for millions of years. We get this last fraction of a second. Just before they come together, they merge into one black hole, and our waveform dies out to nothing here as this thing rings down. So the purple going off into the distance are the gravitational waves propagating out. And that's what we eventually observe. I have another great animation for that, which I'll show you later. Okay, so this is something which maybe you haven't already seen. What I wanted to do with this animation, I talked to newly minted Professor Vitale at MIT and convinced him to make for me an animation in which we're looking at the waveform generated by a binary black hole system, but ramping up the mass of the system. Right? So what I want to show you is that the way we figure out what the source is by looking at the waveform that it produces and then going backwards through relativity to figure out what the masses of the source are. So here you see, as I ramp up the mass of my system that's generating this wave, the frequency is going down, so the wavelength is getting longer. The amplitude of the whole thing is growing, higher mass if you keep it at fixed distance. right? And then this merger over here, I have it at a fixed time, but it's getting lower in frequency. Okay, so the idea here is just to say that we figure out what our source parameters are by solving an inverse problem in which we measure some waveform, and then we match that to a relativity calculation, numerical relativity for this part, post-Newtonian for this part. Right? And that lets us back out the parameters of the source from the waveform.
Is this assuming equal masses?
Yeah, so this one is equal mass, starting with a circular orbit and no spins. So it's kind of the simplest possible thing. That's why I get this nice, simple kind of waveform that just grows. If you have spins, then you'll get modulated waveforms. So you can get things which are much more complicated. But by fitting, in some sense, that waveform, you can figure out what the parameters are that are associated with it. So expanding a little bit the number of parameters we're talking about, these were the parameters for some of the parameters. There are 16 of them, but a few of the parameters for the first system that we detected. And the way that we end up getting things like what's the final black hole spin, some estimate of the distance, things like this, come from this inverse problem solving. So we're using MCMC code, and again, I got Salvo to make this animation where this is the Monte Carlo searching through parameter space to try to find the masses of the source system. You can't see it on here, but this is mass number 1, this is mass number 2, and the point is I go from something which is unconstrained to this little band down here, so I know the two masses lie somewhere in that band. So in a Bayesian sense, we start out with some prior, we end up with a posterior on our masses, which is this little thing here, and then the numbers that we quote are if you take that and marginalize over one mass or marginalize over the other, you get these numbers here. So things you'll notice are that like the error bars on these guys come from projecting this distribution onto one axis or the other. These numbers aren't for that simulation. This one would give a very wide error bar on one mass and a relatively narrow error bar on the other one. But all these things are the posterior of some higher dimensional thing. So don't be surprised by asymmetric error bars or error bars which are much larger on one than the other. Things like that are fairly normal.
So small errors on the spin, the final spin.
Yeah.
You don't fit that, or do you? Or do you just fit the event and then calculate the spin it would leave behind?
I want to say those two things are the same. So by looking at the waveform and figuring out what are the masses of the two things involved and what are their initial spins, you can calculate what the final spin should be. So it's a matter of fitting the waveform to some source model, and then from that you have all of the parameters, including the final spin. It's part of the waveform that you get. That makes sense? Okay, good. Furious agreement. All right. So the very short summary is that the first event, which was kind of the most exciting for everyone just because it was first, but also because it had these very large masses relative to other things that we knew were out there. So we have 30-some solar mass black holes, a pair of them coalescing. Until this happened, maybe people in this room would argue with me, but I don't think most people thought that this was going to happen as a LIGO source. Maybe a few people did. Mostly it was not an expected source. This was sort of a surprise. It was a surprise to me, a surprise to most people in LIGO. I think a surprise to a lot of people outside of LIGO. So these things are out there and they merge in ample time. That's a good starting point. The distance estimate here we get by looking at the amplitude of the signal that we measure and comparing it to our modeled waveform. It's because we figure out the source parameters from the frequency content or the time evolution of the waveform. We know the source parameters. We actually know within the error bars the amplitude of the signal at the source. And we know the amplitude that we measured here. The ratio of those two gives us the distance. So the distance comes out just by looking at the measured amplitude. It's relatively simple. And that's because the source system in the end is just kind of 2 point masses with some spins. Like physically the system has few parameters. So the waveform gets us those parameters. That gets the source amplitude. That gets us the distance. We didn't have rapidly rotating black holes in this first detection. So the spins were not distinguishable from zero. Okay, so I just, interstellar to remind anyone, if you had something rapidly rotating, it's doing something kind of crazy. We weren't at this 0.9, 0.99 kind of thing that you might hear about for black holes should have very high spins. It turns out these really did not have very high spin.
Could they have spin 0.5?
The constraints on the first event were basically that they were less than 0.8 So yeah, they could have been 0.5. The error bars were not great because we have just a few cycles. If you look at the first event, the last few cycles were really quite large, but it was low enough frequency that there weren't many of the cycles before that. And so we wouldn't see any modulation, so we didn't get a lot of constraint on the spin. So we were able to say it's not maximal, but that's about it. The second thing is I wanted to comment about the energy and luminosity of this event, because it's kind of striking. If you take the waveform and you calculate parameters, you can figure out that about 3 solar masses worth of energy went into gravitational waves in this quarter-second kind of time scale. And it's a tremendous amount of energy going out in a very short time. So I calculated a couple of statistics to just try to bring this home. So first one is that our sun has lost 0.03% of its mass in 5 billion years. Right? So here we were talking about 10,000 times more mass in less than a second, or 10,000 times more energy. Another way you can look at this is you can say, take the electromagnetic output of all of the stars in the visible universe and add it all up. And do you get a power output which is higher than this event? The answer is no. This is actually brighter in the sense of just energy output than all the stars added up together. And the last comparison I had was I calculated the luminosity of the full moon at the Earth, and ours was comparable. Again, this is just energy flux kind of calculation. Right? So it's an embarrassingly large amount of energy per square meter coming through the Earth, and yet extremely hard to detect. So it's not the kind of business that you think of when you're thinking of optical kinds of detections. If you have something as bright as the moon and you're not detecting, something's very wrong. Right? For us, we don't have the same coupling constant that you have for electromagnetics. We have G, and that coupling is really bad. So we can have this huge amount of energy, flux, and yet a very difficult detection problem. Okay, the second high significance event we had was somewhat different. So the masses involved were smaller, so 14 solar masses and 7 solar masses, and about 1 solar mass of energy was radiated away. Here we have one of the 2 black holes with a measurable spin. That is a spin which is distinguishable from 0. So it had a minimum of 0.2. And the reason we can make some statement about that is because this lower mass system has many more cycles in the band of our detector. It looks something like this. As the black holes are going around each other, we're getting a signal, and we start out, this is basically the place where our band starts around 40 hertz. So we have many, many cycles in band here, and that lets us make some estimate of things like the spin, which you don't see if you only get this little piece here. So here with a lot of cycles, it means also that you don't have a time series which looks impressive. For the first event, you could take the time series that came out of the detector, do a little bit of filtering on it, and put it on a time trace as if you're looking at an oscilloscope, and you could see the thing sticking out. For this, you need to do match filtering in order to integrate the SNR of all of these cycles as you go along. Right? So it was a much longer sort of thing. You integrate up the cycles, you have a good model, and you get a good signal-to-noise ratio, but it doesn't look visually impressive. Of course, we don't just look by eye at the data to try to find what's in there. We do some complicated statistics, which I won't try to explain. But the first event is over here. This is our detection statistic. Our background is this purple, turning into black as it goes up over here. And this one is in a region where the background just never gets there. So we don't know what the background for that is. We just know that it's very small. So we can say less than 5 sigma. This guy also falls. This is the second event, so the lighter one. And it just misses the edge there. So again, we can't say exactly what the background is for that. It's just very small. If you keep going down, you find that there's a third guy sitting over here. And that one has some quantifiable significance. It's about 2 sigma. So earlier I said 2.8 events was what we detected. This guy is our 0.8 sitting over here. And it's because we can look at this and we can say 80% probability that's real, 20% probability it's not. It could just be a detector artifact. Okay, but 2 very high significance events. If you put these on a plot showing the masses, here's some masses from X-ray studies, just other places where we found black holes out in the universe. They end up kind of here. So these are not so unusual compared to what was known. The first guy was very unusual. Can I claim that we have the only 60 solar mass black hole known?
Yes.
Yes, great. Okay. I mean, known, sort of. I mean, I don't know where it is or anything. If you look at the sky localization of these, there are these enormous bananas on the sky for the various events. And the first one is this guy down here. So this is 500 square degrees kind of thing. So we really don't know. Like, I can't point to a host galaxy or anything like that. I can tell you that somewhere out in the universe, kind of towards the Large Magellanic Cloud, there's a large black hole, but that's about it. Right? These rings like this, or parts of rings, come because right now we have two detectors that are operating, the two LIGO detectors, and you can think of it as just thinking of the relative timing of the signal as it arrives at these two detectors. So this is not really how it's done, but it's conceptually the right idea. If you had two detectors like this and a source that was directly overhead, then as the gravitational wave comes down, it hits these two guys at the same time. Right? So you'd say it's somewhere in this ring. If instead you had a source that was over here and it hits this one first and that one second, which is what happened for the first event, hit Louisiana first, and Hanford 7 milliseconds later, you say, okay, it must be over there somewhere on that ring. And then you convolve that with your antenna pattern and do all the usual good Bayesian sorts of things, you can get these kinds of patches. But these guys were essentially directly overhead, so the timing between the two instruments was close to zero difference, whereas this guy was significantly off to the side.
Knowing the distance,
Mm-hmm.
how many galaxy candidates are at 410 megaparsecs?
Yeah, many, because it's 410 plus or minus 150.
Okay.
Right? And the error bars there come...
Forgot the airport.
Yeah, the error bars there come to some degree from the... You're on some spot on the antenna pattern of the detector, and that changes the amplitude of the signal, but also because the source inclination folds into the signal that we measure. So it puts pretty large error bars on the distance. Yeah, so a very large number of host galaxies. Okay, I couldn't resist leaving this graphic in here. I keep talking about these things as very large, and I have to correct myself briefly. They're not that big, right? That's 60 solar masses worth of black hole, right? And it's really quite small on the scale of stellar type objects. So anyway, they're very massive. They're not very big. I say big a lot, but they're all quite small. And this is the way you can get something at 100 hertz, right? It's because these two guys, about that size, going around each other at about half the speed of light, give you about 100 hertz. Right? You can literally take the Schwarzschild radius and put in half, u over c is equal to a half, and you'll get about the right answer for the frequency. Okay, so they're actually small objects that are extremely massive and moving close to the speed of light. Okay, so that's the first bit of this. I was looking to see how I'm doing on time. I think I'm doing okay. Is anyone dying to ask questions about the first half before I keep going into the second? No? Okay, good. All right, so how to detect gravitational waves. You've probably seen this one before. It's a little bit goofy. I still kind of like it, so I'm going to play it again. These are our black holes going around each other. They merge together. We have gravitational waves ejected out into the galaxy, and they go flying across space and eventually hit us over here somewhere. Ding, there we are. Right. Okay, and the point of this is to say that what we're looking for here on Earth when we say we're detecting gravitational waves is not something complicated. Right? We're looking for something which moves. Right? We're looking, so that kind of looks painful. It's not that bad. But we're looking for some displacement. We're looking for a physical motion of test masses. And for people who remember their GR courses, it was all about clocks and masses. Right? And we're basically doing the same thing. Our laser beams give us a clock in the time it takes for them to go down and back on the arms. And we have test masses which measure, there are sort of inertial references. Right, so this is what we're up to. We're not doing something super complicated. I mean, it's complicated, but not conceptually complicated. So if you take a gravitational wave propagating along the axis of a tube, this would be the distortion it would make to that tube. If you chop off the ring on the end here and just put it out like that, and you stick 4 test masses on it, they would move like this. Okay, so it gets longer like that and back and forth like this. All right, that's simple. We're looking for a motion of these masses. We quantify this by saying we have some displacement on the sides here, and we have some total length. And a gravitational wave will produce a strain. So it's a delta L over L, a fractional change in some measure. And this is a strain just like engineers use strain. If you stretch some material, you get a strain out of it. The kinds of strains we're after are, so again, delta L over L is our strain. Our strain is about 10 to the minus 21. The length of our detector is something like 4,000 meters, so 4 kilometers long. So 4 times 10 to the minus 18 meters. That's the scale we're after. So 10 to the minus 21 isn't totally an accident. That was actually the peak strain from the first event. But it happens to also be the number that people have been using for a long time because they think of a binary neutron star system in the Virgo cluster. It also gives 10 to the minus 21. It's kind of the same value. So, if you look at the history of measuring really small things, you'll find that, Michelson got down to 5 times 10 to the minus 9. But we're getting down to, this little square is 10 to the minus 18. That's the side of a proton, and that's the motion we're trying to measure. Right? So you zoom all the way into your atom, all the way down to the proton, you're measuring this tiny little displacement. Okay, so there's a pretty big ratio here from Michelson to what we need to do. But this was 1887, and we have lasers. So what we're doing in LIGO, basically how this thing works, is we start out with a laser, which is this white can, and we fire our laser beam out. We bounce it off of 2 mirrors, which are our test masses, and we wait for a gravitational wave to move those test masses, and we measure the light which comes out over here. If you put this in terms of electromagnetic waves, you follow these guys down, it's really kind of like a timing experiment. We're looking at the time it takes for one of these wave crests to go down one arm and come back, and down the other arm and come back, and they meet up here on the beam splitter again, and if they've traveled exactly the same time on both sides, we set it up so they cancel here. We have very little light, basically no light coming out this way. When these 2 mirrors move, and remember, the motion of a gravitational wave is exactly this differential motion. I'd put the picture up here again. When these guys move, they change the interference condition and change the power coming out that port. Okay, so this is the simplest possible picture for a gravitational wave detector is just a Michelson interferometer, and distortions like this change the interference phase. So Ray Weiss, back in the 70s, remember this is not long after the invention of the laser, figured out that he could use this new thing called a laser and make one of these laser interferometers as opposed to the resonant bar detectors that were used previously with modest success. Anyhow, use a laser and make an interferometer like this and do much better than Michelson had and much better than Weber had and make something which could actually possibly detect gravitational waves. So from this original design in the early 70s, we went to the LIGO detectors. There are 2 of them. One is in Hanford, Washington. The other one's in Louisiana. Light travel time is about 10 milliseconds from one to the other. LISA's scale height here is about 1.5 meters, so it's a very large tube enclosure going down several kilometers that way. And if you go inside of one of these buildings, we'll do this in a second, you will see some big vacuum tubes or vacuum chambers. And Jamie here is 2 meters tall, so there are 6 meters or so worth of vacuum chambers, those things. It's a very large vacuum system. From Ray's little diagram and the kind of Michelson you might think of for your undergraduate labs, this thing is scaled up by quite a lot. All right, so the next one is new. Let's see if this works. So here's the Hanford picture, and all right. So I got this fly-through animation, which I thought was really wonderful, so let's see if this works for us. We're going to fly into the corner building, and you'll see the vacuum system that the interferometer lives in. Here are big chambers that are about 6 meters high. Jamie was about that high. And the whole interferometer starts out with a laser system. The contrast is not quite there. Starts out with a laser system which propagates through some input optics goes through a mode cleaner, which we use to clean up the amplitude noise, phase noise of the laser beam. We clean up its spatial mode, so we make a nice, round, very stable beam, which we then send into the interferometer. It goes through a telescope that expands it out, and then it heads towards the beam splitter for our Michelson, even though our Michelson is somewhat more complicated. Comes in here to the beam splitter, and then heads off towards the two arms. The interferometer that we're using isn't just a Michelson. It has resonant cavities for the arm cavities. So the light actually goes down to the ends and bounces back, and then it goes back and forth several times. And this lets us take a 100-watt laser that we have at the input and turn it into something like a megawatt of power circulating in the arm cavities. So if we fly down to the end station and go look inside, you can go inside the chamber, and here you'll see what the test masses look like. Strip away the cage, which prevents it from falling. The test mass is a big piece of glass that we bounce our laser beam off of, and it's free to swing front to back. Okay, so that thing can move, and that's our inertial reference. As the light comes back to the corner station from those two ends, it comes back to the beam splitter here and goes towards the readout side. So here we have another telescope and a bunch of readout optics that get us, cleans up the beam again, tries to make a nice clean signal for us. And it kind of all happens on this photodetector. That's where we actually pick up the light. And that's where our gravitational wave signal comes from, just measuring the light intensity on that thing. So you can't see the grid very well. You can just see it under the arms. But the gravitational wave essentially squishes space in one dimension and stretches it in the other, right? And that modulates this light power coming out. Okay, so this is how our gravitational wave detector works. Our measurement of the light power there is this signal that you see here. Right? There's not a lot of interpretation or magic that happens between that measurement and the signal that we publish. Right? There's some filtering, but not a lot more. Okay, so that's the quick fly-through of a LIGO detector. If sound works here, you'll get to hear what the signal from the first event sounded like. And I'll play this, it'll play a couple of times, twice at normal speed, in which it'll just kind of sound like a thump, a couple of times shifted up in frequency. And that's just because the band of the detector is really audio band, but this was the bottom end, and your ear's not particularly good at the bottom end. So I'll shift it up a little bit so you can hear it, and you'll actually be able to hear to some degree the frequency evolution, so the thing chirping up in frequency. Keep in mind that there was really just one wavefront that passed through. I'm going to play it for you a bunch of times, but it was just one thing. Here we go. So that's shifted up twice. This is natural speed. Right. So here's the time frequency plot of what those things look like in the two different detectors, and the two signals from the two different detectors. So you need to take this guy, shift it back by 7 milliseconds, flip him over, and he'll match this guy. The time frequency plots look like this. This one looks a little bit weaker because these things are whitened, and the noise in Louisiana was a little bit higher than in Hanford. So this one's a bit easier to see. But same signal, both detectors. This was really critical for us to have good confidence in the detection. All right, I'm going to play this again, but this time listen to the noise, right? Because that's what I'll be talking about next. The kind of rumbling in the background, that's how I spend my life. Right? Like, the lower the rumbling is, the farther out we can pick up these events. Right? If you had a really bad hearing aid and you were at a party, no one could talk to you, you get a little bit better hearing aids, you can hear the guy who's standing next to you, you get a really good hearing aid, you can hear someone on the other side of the room. Right? That's what we're up to. So when you're someone like me who's been working on the LIGO detector for 20 years, you spend a lot of time thinking about sensitivity curves like this. So this is, again, audio band, so 10 hertz to 10 kilohertz, really the same range as your ear. And our best sensitivity is right through the middle, again, pretty much the same as your ear. At the low end, we lose sensitivity because of everything on Earth moves around at low frequency. So down here, things are kind of hopeless. Here, we're limited by quantum mechanics, really just detection of light and some thermal noises. And this is also just photon statistics up here. I won't go through the litany of noises because I want to talk about other things as I go along in the talk. But this is how we quantify our noise, and my objective in life is always to push that guy down. Right? That's what I'm trying to do. This is some measure of our success in doing that. The initial LIGO detector, the initial LIGO detector is the green one, and it needed some help. We did a lot of improvements to get that up to the advanced LIGO detector. Our first run, 01, in which we made our detections, are the pink and red guys on there. So we had moved down by a factor of 3 or so up here, but the real win in terms of binary black holes is this difference. Right? And there we won a lot in terms of the sensitivity. Turns out I carry extra batteries because I know something about lasers, which is they tend to die. So speaking of that, our progress since this red curve, which is 01, was essentially negligible, exactly because our laser died, which I talked about earlier today. So I won't talk about 02. 02 is pretty much the same right here again. Where we're going in the future is towards the design sensitivity here. All of this stuff is shot noise up here, this nice smooth thing, and this is just turning up the laser. Right? That's all that is. Some of this stuff over here is also quantum noise still in the bottom, and improvements over here will be work on technical problems. So just other garbage in the detector which makes our sensitivity not as great as it could be. This is where we're headed over the course of the next couple of years. And I'll get to this one in just a second. Here's what this signal from the detector sounds like if you don't filter out the lines or anything like that. Just listen to the whole thing. And what you hear are these little line harmonics going on in there. Whereas previously we had notched them out. They're very narrow, so we can take them out. Right? And this is, if you were sitting in the control room, just listening to the detector as it was operating, that's how it sounds. Right? And this is, to me, this is kind of a happy sound. I mean, the interferometer is locked, the control system is going well. My thesis title was Lock Acquisition in Resonant Optical Interferometers. It means I spent a lot of time just trying to get the control systems operating, everything going. So that's a good, happy sound. The thing is working properly. So 20 seconds into this, the word thump will appear down here. And then if you listen really carefully, I notice your speakers are good enough that you should be able to hear something happen. So that was our first event going by in its natural form, right? So if you just took the signal coming out of the detector, you put it on a speaker, and you're sitting in the control room, if you were really paying attention, you would have heard it go by, right? It was that big, so really obvious. That's not been true for any other since then, again, because there are many more cycles, and you really had to integrate it up to hear it. Okay, that's enough fun with sounds. So going from initial LIGO to advanced LIGO was some major improvements in hardware. We got these great isolation systems. We got big optics with wonderful coatings. We got this big scary laser. These things are all installed and pretty much operating the way they ought to be. This guy we're still working on. And the blue curve you saw earlier was almost a factor of 3 below our current sensitivity. Right? So without making big design changes, just working our way towards the nominal design, we should be able to gain about a factor of 3 in sensitivity. A lot of that's laser power technical noises. The reason why, a factor of 3 might not sound like a lot, but we win with the sensitivity cubed, right? And that's true because if we're here, we have a binary black hole system at 400 megaparsecs, and if you move it 10 times farther away, it just moves down by a factor of 10 on this plot. Okay, so as we improve the sensitivity, when we get to design, we'll be able to just barely hear something like the first event out to 4 gigaparsecs. If you think of that in terms of the volume of space, right, this is us, galaxy, this is initial LIGO range, the green curve on the earlier plot. This is initial LIGO compared to advanced LIGO. Right? The volume in space is going with the cube of that distance. So we actually win a lot with this factor of 3. We win a factor of almost 30 in terms of our detection rate with that factor of 3 improvement in sensitivity. And even if you see something which looks negligible, like we got a factor of root 2 improvement in sensitivity, that's still a factor of 3 or so in rate. It's not a small thing. So we work very hard for relatively small factors in terms of the sensitivity. Okay, so how I spend my time when I'm at MIT. So I'm really looking at the most immediate future. What are we going to do next year to try to make the instrument better? The answer to that is basically squeezed light and quantum noise reduction. So that's what we're going to try to do next year. Turn up the laser power, get the squeezers, things like that. What are we going to do further down the road? Well, later down the road, we can hope to change the optics, improve the coatings, reduce the thermal noise. Right? So that's 5 years down the road. If you go farther down the road from there, you strip out everything out of the interferometer, you put in a whole new system, you make it cryogenic. Right? That's maybe 15 years down the road. If you look farther down the road than that, you say, really, at that point, we're at the limit. We need to build a new detector. Right? We need a new facility. So I want to talk about that last part because there's some exciting stuff in there, which I think is relatively new. Not all that long ago, I put this paper on the archive, which describes where I think we can go with new detectors. So if we were building new LIGO detectors, we would make them bigger. Obviously, that's sort of the name of the game here. Remember, delta L is equal to strain times L, where L is the length of the thing. If I make it 10 times longer, my signal is 10 times bigger. Right? So you like to push length on these things. Advanced LIGO is up here. The best we think we could possibly achieve in the current facility is this guy. If we push that out to a 40-kilometer detector, we end up down here. Okay. This ratio is large enough that we end up kind of out to high redshift for our binary black hole systems. Again, I spend my time thinking about how to make this happen. So this guy here, to me, looks like a huge win over advanced LIGO. And we can quantify it in terms of how far out can we detect compact binary systems. So on this axis, I've put the total mass of my compact binary system. Again, I'm assuming circular orbits, non-spinning, equal mass, the easiest possible thing, but just to give me a figure of merit. And on this axis, I have the redshift. And what this guy is supposed to say is this is the horizon, so the maximum distance at which we could possibly detect a system with this total mass using advanced LIGO. Right? So if we had a system with a 100 to 200 total solar masses involved, advanced LIGO could get out to a redshift of 2. Right? If you take the ones that we actually had, there would be 60 on here. We could have gotten almost to a redshift of 1 with those guys. Right? That's what this thing is supposed to say. And this is absolute maximum, so perfectly oriented, directly overhead, can't possibly do better. That's this thick curve here. Binary neutron star systems, not so far. Right, they live over here. And then these color gradients are supposed to show you different fractions. So into here, it would mean that 10% of systems live inside of this. Sorry, 90% of systems live inside of that, 10% live outside. And in here, there's a 50-50 chance that I'll get it. And then you can't see it because the projector won't quite make it. There's a lighter one that is 75. Right? So these are the absolute maximums, and then what we could do inside of that. If we go to this next generation of detectors, then we should be able to detect things out to a redshift of something greater than 10, right? So kind of redshift of ridiculous over here. You get to some very large redshifts, and there's probably nothing out there to detect.
So why do these curves flatten out or even fall off?
Why do they fall off over here? Yeah, so this side of the curves fall off because the noise curves come up at low frequency. We have this rise at low frequency. And as you make systems more massive or put them at higher Z, then they just end up producing, the end of their waveform can be here. Right? And as soon as they move off the bottom of our band, these guys fall off on that side. And that's why you see there's very little gradient here, these different percentages. It doesn't matter how far away it is so much. If it's too massive, it's just too low in frequency. All right, so we can get out to high redshift for these things. And that's nice. And it's high enough that if these black holes are coming from stars, then we can potentially detect compact binaries from everywhere in the universe, everywhere where they might exist. Having gotten my paper out on the archive, people started looking at it using those curves, which was exactly the idea. I'm not great at astrophysics. I know about the instrument, but there are people out there who know about astrophysics. So I grabbed one of the recent papers to appear on the archive that was using these noise curves. And I just they talk a little bit more quantitatively about the statement I just made. We can detect things from all over the place. So here we're moving from the present. I added the arrows. We're moving from the present 01, 02 to this thing out in the future, Cosmic Explorer, CE. Right? And that's this progression of sensitivity getting better, like this. So going from now to the 2030s. And their prediction is that our event rate for these future detectors would be almost 1 million per year, right? It's huge. Some huge event rate. If you go to their most pessimistic model, this one which has high natal kicks, you're still talking about 10 to the 5 kind of number, or several 10 to the 4, right? Some very large rate in terms of event rate per year. If you down select only to high signal to noise ratio events, so they're looking at things where you can resolve the ring down part of the waveform. So just high signal to noise ratio, you still have thousands per year, right? It's a huge event rate. It's really a different regime than the one we're used to operating in which every event is somehow precious because you only have 3, right? Here you'll have this population and lots of events to play with. And then to spread that out in terms of what redshifts you actually are getting signals from, the answer is mostly around a redshift of 3, sort of 3, 4, out to 5. This is where the dominant population is. A lot of things in that region, but out as high as a redshift of 15. That's what they predict. Okay, so a lot of events from all over the universe if you have one of these big detectors. I'll say that there's not a lot of, I'm not making huge speculations about the technology in these detectors, right? You could make something, actually the one which is this CE1 guy, which is not so different from the other ones. It's different, but not so different. That's using today's technology and just making the detector bigger, right? So it's about plumbing and dirt moving, right? That's what you have to do. That's what costs the money. But using today's technology, we can already get these really amazing event rates, huge numbers of detections, and some with very high signal-to-noise ratio. The other thing that will be happening as we move into the future is we'll get more detectors coming online. So I've talked a little bit about, we have 2 detectors in the US. I've talked a little bit about Virgo, which should be coming online soon. I was asked about Kagra. Soon this guy will be on. In Japan, soon being a few years down the road for Kagra. LIGO India is scheduled, should happen. We're told that it will happen. The best date we can put on is 2024, 25, 26, something like that. So mid-2020s to have LIGO India online. So there are a number of detectors that will be coming up as we go along, and this will make our sky localization better and better. So we hopefully go from these big bananas in the sky that are very hard to search in a useful way to tens of square degrees or fewer as we get more detectors going. When you go to 3rd generation detectors, if you have several of them scattered around the planet like this, then you can start getting sub-square degree measurements for some of the events, the ones that are high signal-to-noise ratio. Before I wrap up, I should say that there's a lot of stuff I didn't talk about here, right? I was talking about my particular favorite detector and my favorite sources, right? But there's all kinds of other stuff going on in gravitational wave detection. So different technologies that are out there. This is pulsar timing, space detectors. There's lots of other stuff happening, which I'm less knowledgeable about, so I didn't want to talk about that. And looking for all kinds of different sources, right? So just to be fair, and keep in mind there's a lot of stuff which I avoided, not because it's not great, but just it's not mine. And I also didn't talk much about multi-messenger astronomy, but this is something which is becoming more and more important. And I think that I was asked earlier about binary neutron stars, so I felt like I should throw this in. As we start getting binary neutron star systems detections, which probably won't happen for another few years, but when that starts happening, and we have the possibility of getting electromagnetic signals from these sources, I think there's also a lot of work that can go there. I didn't want to talk about any of that in this talk. I think probably the people in the audience are more knowledgeable than I am, so there's that. Okay, so the conclusion, big picture message here. First thing is that kind of surprisingly, GR is right. And I say kind of surprisingly because if you go from what we knew before this detection to what we know now, there were many orders of magnitude in field strength that were covered there. We went from weak field to strong field. And it shouldn't have been taken for granted that was going to work. I think most of us thought it was going to work, right? But most physical theories don't survive 10 orders of magnitude of extrapolation. So that was actually kind of impressive. Large stellar mass black holes exist in binaries and they merge, right? Not a trivial conclusion. I think now we all kind of feel like, yeah, okay, of course. Why not, right? But a few years ago, a lot of people said, no, that doesn't ever happen. Non-trivial for me, having spent a lot of times working on this, is yes, these detectors actually can work, which again is something which now, fine, take it for granted. A few years ago, I would be regularly made fun of for working on such a thing that was never going to pan out. So that's great. The important thing I think for this, important thing for this crowd is that we're really just getting started, and we're making plans for what to do in the future for our detectors. And the more feedback we can get from astro people who actually know about the sources we're looking for, the better off we'll be and the better plans we'll make. So if you are thinking about how gravitational waves from black holes and neutron stars and whatever source you can come up with are going to impact your work, and getting that back to us, that will really help us build better detectors in the future. So we have an opportunity right now. We're in this sort of design process of figuring out what we're going to do for the next 20 years in detector land. The more that you can write about these sensitivity curves we publish, the better off we'll be. So thank you all.
Thank you, Matt. Time for questions. Yeah, Lisa.
I'm wondering, is there a peril to too much sensitivity? In the sense that, for example, if you're getting a rate of 1 million per year, you'll have simultaneous signals, and will you be able to untangle them? And also, will you be sensitive to things that are passing through your frequency band long before merger? And you're not going to see the merger, you'd need something like LISA for that. But now, because you're so sensitive, you're picking that up as well.
So there's, first, I think it's been studied fairly carefully, and it looks like you can take multiple signals that are overlapping and generally remove them effectively. But a really short answer is there's 3 times 10 to the 7 seconds in a year, and if each one of these things is a second long, and you have 10 to the 6 of them per year, you still don't have a lot of overlap, right? So they're short. Even 1 million per year is still only 10% of the time. And then, of course, as you make the mass lower, the signals get longer, and that equation changes, and you have to ask yourself if you remove them. So the story is more complicated than that. But the very quick numbers answer is it shouldn't matter so much.
So the question about expanding the interferometer, you bounce the laser back and forth on it. How many times does it go back and forth?
A few hundred. It's a resonant cavity, so it's not an integer number. It just goes around.
So do you have to go longer, or can you just increase the diameter? I mean, I'm just trying.
So the size of the beam is important only, well, and there's a geometrical limit just due to optics of how small you can make it. But we actually make it bigger than that. We do that to average over the surface of the mirror, and we do that for thermal noise reasons, right? The molecules on the surface are wiggling, so we want a big beam. Otherwise, the size of the beam doesn't really, the cross-section doesn't matter too much for us, for the beam. We can increase the finesse of the cavity, so make the light just go around more times, and that gets us more signal. But you might have noticed that my sensitivity curves went up, have this sort of rising part on this side, and that's because we're integrating out our signal. So the longer you keep the arm going, or the light going around in the arm, the more you integrate out your signal. So that's one reason. The second reason is that any disturbance which moves the mirror, right, any displacement noise that you have, if you go around 10 times as many, you have 10 times as much sensitivity both to gravitational waves and to all of your displacement noises. So you didn't really win anything there. Right, so longer has this advantage of taking all the displacement noises, things that just move the mirror, and making them less important by the ratio of the length.
So in the case you have median detections, I believe you have several detectors. What is the spatial precision that you would get to detect, to locate the events?
In the case in which we have how many?
Like the ultimate case, you said 1 million detections a year. Like, how well could you locate these events?
So so it kind of depends on how many detectors you assume we have operating, but if you look at 2030 something, we'll probably have 4, maybe 5 detectors operating. If that's your assumption, then the few very high signal-to-noise ratio events could be very well localized, sub-square degree kind of localization. Of course, that's very good. And a lot of them will be relatively poorly localized. I think that this was studied in some detail, and there's at least one paper out there which tries to quantify the number of galaxies, number of host galaxies in the error box volume if you had a future detector network. And it starts to approach 1 as you get to these third generation detectors. You have 4 or 5.
Well, are you currently set up to discover unanticipated waveforms?
Yeah, so I've been talking about these compact binaries, which we can predict waveforms for. We also have what we call a burst pipeline, so it's looking for unmodeled sources. And that's really a cross-correlation between the 2 detectors. So we're looking for something which looks like kind of the same waveform and appears in both detectors within the light travel time window between the 2. So yeah, we'll pick them up. And in fact, things like the first event were picked up by both of these pipelines, actually by 4 different pipelines, because we each one. But the unmodeled search also finds these binary signals if they're large enough. So the first event was picked up by that one as well, with not quite the same signal-to-noise ratio, but almost as good, because it looks kind of like a burst. Whereas the second event, which was high significance for the compact binary search, was not as high for the unmodeled search, because you really need to integrate it with the waveform to get the high significance. So we have the searches running, but not as good if you're looking for a source that you actually know.
So would it help you localize more events if there's a southern hemisphere detector? I mean, right now they're all kind of
Yeah, right. So if you can get them out, the more out of the plane they are, the better off you are. The original idea with LIGO India was LIGO Australia. It turns out that Australia doesn't have many people. It doesn't have much money, which means it couldn't manage this and the SK at the same time. So yeah, the first idea was actually LIGO Australia. That's better than India. India is the best we could come up with.
Can you do LIGO Antarctica?
You don't have to worry about energy.
Yeah, right. So, yeah, I mean, just to be a little bit funny, the truth is that people have thought a lot about where to place detectors, and they often base their decision on what would have the lowest seismic noise or things like this, kind of nice science type criteria. But you need to get people to work on these things. And we already have a problem that they're in Hanford, Washington, or Livingston, Louisiana. It's like, look, you want to go spend 6 months living in the swamp? No, right? So you want to actually put detectors in places like Pisa. It's a nice town, there's good food. But seriously, you have to get people to work on detectors. So I'm afraid that the Japanese will have trouble with their underground detector because it's in the middle of nowhere and everyone has to work underground. Right? And people are already saying, look, this is depressing. Right? But you need to get graduate students who are going to go and work 18 hours a day, 6 days a week to make these things operate. And you can't do it if you're in some totally remote, horrible place.
So no detector on the moon.
I have a simple technical question. You're putting 100 watts into the cavity. I assume something like 100 watts is coming back out of the cavity. Maybe a little bit of losses somewhere, but
a lot of losses.
A lot of loss. Okay, so I guess my question is, you're sending almost no energy to the actual photometer, which I guess means the rest of it goes back into the laser.
Yeah, no.
So what happens to that energy?
See if I can find a diagram with the right level of simplicity. The idea of these detectors is that they, let's see here. The idea is that we have a laser light coming in. There's actually another mirror here which you're not seeing. But we try to mix it so this whole resonance system has a loss, which matches the input mirror transmission, so that the laser light is what we call optimally coupled into the interferometer. And if you do it right, you end up with 100 watts coming in this way and close to 0 coming back towards the laser. And all of the light, the 100 watts that you're missing is coming in here. You get a large amount of light circulating here, and there's some scattering off of that. So you'll have light which is lost in the arms, you'll have light which is lost in here. So most of the light which comes in gets lost somewhere in the interferometer, either due to absorption or scattering. And as you say, a tiny amount of that will leak in this direction. So a few hundred milliwatts.
I would have thought that the sensitivity of your measurement, because it's all about how well you can measure off the photodiode. So I would have thought that you really want the energy to be coming back to the beam combiner.
Yeah, no.
Otherwise, you're not measuring anything.
No, what we want is we want the power to be high on the emitters, because when the gravitational wave comes by and or whatever moves this guy, when it moves this, what it's doing is effectively making audio sidebands on this light, and those sidebands are proportional to the light amplitude of the power that's hitting this mirror. If we can couple those guys effectively to the output, right, then you're comparing those audio sidebands to your quantum fluctuations at this detector, and then the little bit of light that you're leaking is just a local oscillator for making that measurement. And that local oscillator mixes with your vacuum fluctuations or your quantum noise in the same way it mixes with the signal. So our signal to noise ratio here doesn't really care what this amplitude is. We make it just large enough to get past our technical noises, and that's it.
It does.
How does the sensitivity change when you go to extreme mass ratios, like I know stellar versus 10 to the 6 dipoles?
Yeah, so anything in which the large mass is too big for us will fall off we just fall off the bottom of the band. So if you have something with a 10 to the 6 solar mass black hole, then your other object can't go around it 10 times per second.
Sure, but will it be possible to detect it with space-based stuff, with laser?
Yeah, so
Flies, or when it flies?
right. Often the signal gets weaker as you go to these large mass ratios. And so you put everything in terms of short mass, and you find that you're not winning nearly as much as you'd like to when you have a large mass object and a small mass object. But yeah, they can be detected. One of the things that the LISA space detector is after are these things called MRIs, which are extreme mass ratio inspires. So yeah, it's an interesting source. For LIGO, not so much, but more for LISA.
So I have a quick question, and we'll come back to a few more. So you said that the sensitivity goes with the length of the detector, right? Does the cost also go linearly with the length of the detector?
No. The sensitivity isn't really linear either. So the first approximation is this one, right? When you put the L over there, you say it's linear. But it turns out that the thermal noise in your detector depends on the beam size, and the beams grow as you make it longer. So you're actually winning faster than linear. Quantum noise, in order to keep, this part will move linearly, but in order to keep the bandwidth the same, you have to reduce the finesse of the cavities. So with the quantum noise, you're actually winning with the square root again, right? And that's this part. So the two most fundamental noises, neither of them are actually linear, right? It's just the very first thing you think of is this, and that's linear, but not really for the detector. The second half is the cost, and there are a bunch of fixed costs just with the facility. Few hundred million, something like this, fixed costs, and then you get costs associated with the tube. And once you get to 10, 15 kilometers, maybe those things start to balance. And then as you make the tubes longer, then your tube cost starts to win. The thing that happens there, this is really just dirt and plumbing. The thing that happens is the amount of cut you need is growing with the cube of the length of the thing. And you have to cut the Earth out and move it to the ends to fill. So you end up with a cost scaling roughly cubically with the length once you get to that point where the cut starts being important. Right? So around 40 kilometers, the cost just starts to explode. That also happens to be about the length at which this corner starts to really get pushed down into your seismic noise at the bottom end. So the reason why I pick 40 kilometers is because it's a nice kind of sweet spot in which this frequency hasn't moved down too much, and the cost hasn't completely blown up.
What sort of cost?
The right answer,
2 billion, 4 billion?
Yeah, right. So yes. The right answer depends heavily on the geology where you decide to put the thing, because you do a lot of earthwork. The best round number I can give you is 1 billion for a site, right? But that could be lower by a factor of 2 if you find a place like Carson Flats, or Carson Sink, whatever it's called, that's kind of bowl-shaped already, right? Then you win a lot. If you have a place instead where you have to dig through a lot of rock, then it will cost twice as much.
And remember, you want 5 of them.
We don't need to build 2. Someone else can build the rest.
Yes.
So what's the current status and observing plan now?
Current status and observing plan right now is we're running right now This is O2, second observing run. This will go until late May, something like that. Hopefully Virgo will join us at some point, probably towards the end. And then we'll go down for 9 months to a year. We'll come back up, we'll run for O3 for probably about 9 months, something like that. Sensitivity should be something above 100 megaparsecs for O3, best guess. So we'll continue this cycle of take the instrument down, work on the sensitivity for several months, bring it back up, run for several months, go back down, and just repeat until we're close to design sensitivity. And we have some upgrades that are, actually I promised to talk about this and I didn't do that. The light blue curve in this one. So we have some upgrades that we're working on at MIT and elsewhere that'll let us push past design. So those will also kind of be going in simultaneously with this work. So we might not ever actually hit design with the design. We might try to, scooch on past that and get that over here somewhere. But it'll be a lengthy process out into 2020 or so.
A question left over from your lunchtime talk. During the near-term downtime, you listed a number of improvements, but interesting to me was that you listed them by site. And to first order, I might have thought that these are totally identical systems and that what improves one would automatically improve the other. So the fact that there are distinct improvements by site, is that reflective of the fact that they're not exactly the same, or that they have individual personalities that require different tweaks?
Yeah, so to the best of our ability, they're identical, but they're not. So we end up doing somewhat different things with two different observatories. A lot of times the things which separate the sensitivity we have from the sensitivity we would like are things which have to do with the personality of the instrument. And that's mainly down here, these things I call technical noises. A lot of those are things which shouldn't be there according to the design. There's no reason why you would expect the junk to be the same at both sites. So the junk is often different between the two. Some of it's the same, but a lot of times our technical noises can be very distinct. And they can require distinct solutions. Sometimes this comes down to, just you can't make the two observatories the same because one is in Louisiana and the other is in Hanford. The Hanford site is sitting on bedrock. It has high winds. It has relatively low microseism. You get just sort of different environmental conditions for the two of them. And that means the seismic isolators are tuned differently for the two different sites, and that can end up impacting things farther down the chain. So there's stuff which is really irreducibly different, stuff that we can't change just because they're physically in different locations. There's other stuff which is just different by happenstance. But the interferometers were constructed to the best of our ability identically, but maybe when you align one, you end up with some light which is scattered off of some screw head somewhere that you didn't think about, right? And it's bothering you in one interferometer and not the other, right? And it's one of those things that happen by chance. So there are both kinds of differences.
Right. One last question.
So when Ray talked here yesterday, you're talking about these curves just marching down one way or another. You're going to beat them down there, right? Okay, I get it.
We've always done it.
Yeah, right. You've always done it. But Ray was actually very cautious yesterday in saying that it looked like maybe, I don't want to misquote him, that there was a fundamental problem that is unknown. Its solution is out, just completely out in the vapor. Yeah. So is this something that? What is your view of his caution?
I'm more optimistic, but I wouldn't say that he's wrong. But I would say that there's always a mystery noise, right? And Ray can get excited about some mystery noise because it's a mystery noise, and oh my goodness, what if this is really fundamental? But all throughout these things, there's always some little junk over here that we don't know what it is. Right? That's always been true since initial LIGO. For the last 20 years I've been doing these things. We've always had some little mystery thing that we worry is fundamental. And eventually we figure out what it is, and we fix it, and we keep going. Right? So I can't say that he's wrong, but I'd say I'm not the least bit surprised by the current situation, nor am I really all that worried about it.
Pessimism versus optimism.
Yeah, right.
Youth versus age.
Maybe it is, right? It's like I've been doing this long enough to feel like we can just keep doing this, right? This was also something that we didn't know what it was right? But eventually it went away and we got down here. And sometimes you have to go make some big changes to fix things. But we managed to overcome these problems. Now, so there might be something really truly fundamental that we've missed. I can't say there isn't. But I don't have any reason to expect in the current situation that there's a fundamental problem.
All right, and on this optimistic note,